Section 9.1, one-to-one functions. Just as a recall, the definition of a function, each input has exactly one output. In some functions, different inputs correspond to the same output, and the definition is given. A function is a correspondence between the domain and the range such that each member of the domain corresponds to exactly one member of the range. If it is possible for a vertical line to cross a graph more than once, then the graph is not the graph of a function. So visually, we can use the vertical line test to see whether a relation is a function or not. If a function is one-to-one, then its inverse correspondence is also a function. Well, for a function that is one-to-one, different inputs have different outputs. And here we have the definition, as I just said. If the function is one-to-one, then its inverse correspondence is also a function. For a visual check to determine whether a function is one-to-one, we have something known as a horizontal line test. Very similar to the vertical, only a horizontal aspect. And it states, if it is impossible to draw a horizontal line that intersects a function's graph more than once, then the function is one-to-one. For every one-to-one function, an inverse function notated by f to the negative 1, that's the notation for an inverse function, it exists. So we actually have two methods, as it turns out, to determine whether a function is one-to-one. One method is to perform the horizontal line test. The other is to try to find the inverse. If it's possible to solve uniquely for y after x and y have been interchanged, then the function is one-to-one. And we'll take a look at that in the next video. But in the meantime, let's check for one-to-one functions on the following examples. We're given the following function. It is of the form of y equals mx plus b. It's a linear equation where our slope m is equal to 1, which is the ratio of rise over run, and we would have a denominator of 1. Our y-intercept is at the point 0b, and for this to correspond, a minus 6 is the same as plus a negative 6. Our y-intercept is at the point 0, negative 6. So to graph that information, we'll start with our point, moving away with the slope, up 1, over 1, up 1, over 1, and then connecting those points for the graph of this linear function. So we clearly have a function. If you drop the vertical line, it's only intersecting one point, but more to what we're being asked, is this a one-to-one function? Visually or for real, plot a horizontal series of horizontal lines. As long as we only intersect one point, and in every one of those cases I am only intersecting one, it passes the horizontal line test, the HLT, horizontal line test, which means, yes, it is a one-to-one, and we could then find the inverse. In this next problem, we're given the following polynomial function. This is of the form a times x minus h quantity squared plus k. It's going to graph into a parabola. Our leading coefficient is 1. It's opening upward. Our vertex, which is at the coordinate hk, will be at, since nothing is being subtracted from our x before it squares, it means our h is 0, and instead of a minus 3, we can turn this into plus a negative 3, giving us a k value of negative 3. To graph this parabola, we need another point along with our axis of symmetry, which is x equal to 0. The one point that's real easy to find is our y-intercept, and generically that's 0c. So in this case, that will be at 0, -3, which is also our y-intercept, or our vertex. So plotting the point 0, -3, our axis of symmetry is going through here, and unfortunately, because our vertex is our y-intercept, we do need to find another point to get a sense of the graph of this equation. And graphing this, say we let x equal 1, plugging it into the function to find the corresponding y value, we will put 1 in. That will give us a 1 squared minus 3. 1 squared is 1, minus 3 gives us a -2. So the point 1, -2, if we reflect that, we will also have this point. And just for a rough graph then of this quadratic function, we have the following. It is a function, as the notation is saying, it would pass the vertical line test only intersecting 1, but we're being asked, is it a 1-to-1? And to do that, since we have worked to find the graph, we will draw a horizontal line test, and we only need one horizontal line test to fail on 1-to-1, and there it is. In any series of horizontal, we're going to intersect in 2 points. So this is failing the horizontal line test, which means this is not a 1-to-1 function, which means it doesn't have an inverse. Here we have another function given here. May not be familiar with this, but a technique is just a matter of graphing some points to find the values. So let's let x equal 1. We will have 3 to the first, which is 3. Let x equal 2. 3 to the second would give us a y value of 9. Obviously, the greater our x is on the positive side, this is only heading out towards larger and larger y values. So let's go with smaller. Anything to the 0 power is 1. If we let x equal a -1, we're going to end up with a 1/3. If we let x equal -2, we will have 3 to the -2, which negative exponents we can drop to the denominator, which is going to give us 1/9. And as our x gets smaller and smaller, we are going to get smaller and smaller y values. So if we plug what we have on the graph, we have the point 1, 3. We have the point 2, 9. There's 7, 8, 9 heading out there. 0, 1 was another point. We had -1, 1. I didn't plot the right point, did I? 0, 1. 0 out and up 1. There we go. -1, 1/3. -2, 1/9. It's getting closer and closer to our x-axis. But if we connect those points, the value is going to get closer and closer and closer, but not take on the value, slowly approaching. Checking our horizontal line test for our 1-to-1, everything looks fine. And even though this, you may say, oh, we're intersecting, they are gradually, there's no width to our line. These values are gradually getting smaller and smaller. It's passing the horizontal line test, the old HLT, which means, yes, there is a 1-to-1 relationship here and would have an inverse. In this last example, they're asking us, does this function have an inverse? And to determine whether it has an inverse, we need to know if it is a 1-to-1 function. This looks somewhat, to get rid of our function notation, let's set it equal to y. And if we temporarily ignore the absolute value and think of this as y is equal to x plus 1, it looks like a line. And as a line, in slope-intercept form, we can recognize that our y-intercept is at 1. We have a slope of 1, so up 1 over 1, up 1 over 1. And we could plug those values in, and this would graph up here infinitely, and it would graph here. And I have read ahead and familiar with this, so I'm going to dash these in. But we aren't dealing with just this equation. We're dealing with the absolute value of this as well. So just to show what's going on with these values, let's set up a table for this function and pick some of these smaller values. When x is equal to a 0, the absolute value of 0 plus 1 is going to give us 1, and we have that point. When x is a negative 1, we would have negative 1 plus 1. The absolute value of 0 is 0, so this point is going to be okay. When we let x equal a negative 2 plus 1 gives us a negative 1, but the absolute value negative 1 is 1 and not the negative 1 that we were headed for. So instead of here, our point actually will be at negative 2, 1. Let's put another value in just to illustrate that. The absolute value of x, which is a negative 3 plus 1, leaves us with a negative 2. The absolute value of negative 2 is 2. So the point on this function would be negative 3, 2. Negative 3, 2 is here. So instead of continuing on, we take an abrupt 90-degree shift, and the absolute value of this function or this equation ends up having this V shape to it. And to answer the question, is this a one-to-one function, you can easily see any horizontal line is going to intersect in 2 points, and so it fails the horizontal line test, which means it is not a one-to-one function, which means there isn't an inverse.